Hello, and in today's calculus lesson, we're going to take a look at a problem involving position, velocity, and acceleration, where you're given a position function and asked questions about the velocity and the acceleration. I'm going to use the methods of calculus to do this. This differs a little bit from algebra-based physics class problems because the particular function we're going to be dealing with doesn't have constant acceleration, so you can't just use those formulas you might have learned in high school physics. So let's take a look. This is problem 20 from our textbook, and it says, suppose the position of an object moving horizontally along a line after t seconds is given by the following functions. S equals f of t, where s is measured. Now, s is typically what we use. This s here usually means position. That's our function. S is measured in feet with s greater than 0, corresponding to positions to the right, and t is in seconds. So since this f of t is our position function, that represents feet. But when we find the velocity, that'll be in feet per second. And when we find the acceleration, it'll be in feet per second squared. That's what the helpfulness of this is. Now, we are asked to graph. So we have a position function that's negative 6t cubed plus 36t squared minus 54t. And what this means right here means we only need to look from times 0 to 4. We don't have to look at the entire domain of this polynomial, which would be all real numbers. We only care from 0 to 4. So the first question says graph the position function, and I've written that down here. So in order to graph a function manually like this, and the functions in the text are selected such that they're very factorable, what you really want to do is you want to find the zeros first. So in pre-calculus 1, the way I teach it is you find the zeros and you put the zeros on your graph. So I have a 0 at, let me change my color here. I have a 0 at t is 0. And a 0 at t is 3. Oh, wait a minute. I have a repeated 0 at t is 3. And it's repeated an even number of times. There are 2 zeros at t equals 3. So what that means is my function is not going to change sign there. I'm just going to touch t equals 3 and turn around either from this direction or this direction. But then the way I figured out which direction I'd go to it, I'd be able to look at the end behavior. So our function was a cubic. The highest degree was 3. With a negative leading coefficient. And to find the ends of a polynomial, or to find the limit as x goes to negative infinity and the limit as x goes to infinity, which is what you used to call end behavior before you took calculus, you compare it to a similar polynomial, and you look at the degree. The degree is odd, so the polynomial I'm going to compare this to is x cubed, and then you look at the sign of the leading term, and it's negative, so my ends are going to behave like the ends of negative x cubed. Well, x cubed would go down to the left and up to the right, so I'm going to do just the opposite. Negative x cubed. If you graphed x cubed, you would get something like that, although you wouldn't have really a bump there, you'd have a seat. But I have the negative of that, so this end has to go up and that end has to go down. Now I've graphed all my zeros. My function cannot change sign or cross the x-axis anywhere to the left of this 0 at t equals 0. That's the last time it can do that. So this must be where it goes off to the left end behavior. So I can sketch that end. And then because t equals 0 only occurs once, I actually know I do change sign. If I go from a number less than 0 to a number greater than 0, my function will change sign. So I go down. But then I got to come back up, and it's not very nicely rounded, but it doesn't need to be. It can be a rough graph, and in my math lab, you're usually choosing these. So let me make it a little nicer. Oh, sorry, I did not pick the eraser. Let me make it a little nicer here. So I kind of want to come back to this 3. This is my 3. This was my 0. This was my 3. I want to come back to that. But at t equals 3, so this is my t-axis, and this is f of t, and this is in feet. And this is in seconds. At t equals 3, I'm not going to cross the axis because that's a repeated root. It will not cause the sign to change. If I put a 2 in, for t, or if I put a 4 in for t, I will still have the same sign. It turns out that sign will be negative. 3 is my last 0, so I know that's my end behavior. So this is approximately a graph of my function. Now, you can also use your graphing calculator to take a peek at this. I'm not going to tell you you can't do that. The only thing I am going to tell you is the rest of the problem must be justified showing work using methods of calculus. Because basically, you could use your calculator to graph all of these, but it doesn't show me you know any calculus. But it's not, in your homework, that's certainly a way to check or to get clues. You probably don't want to do that during the test also, because backing out of looking at the graph and then making the work will take you too much time. You need to just know how to do the calculus methods right away. If you have time to check later, then you might look at the graphs in your calculator. But this is part A, how to graph that position function. So now that we've graphed the position function, I'm going to move on. I repeated the function here just so I could see it when I'm talking to you. They asked me to find and graph the velocity function. Well, first, we're given a position function. This f of t is a position function. So we have to find the velocity function. When you have a position function, the velocity is the first derivative of position. So let's see, negative 6t cubed, I'm going to use the power rule. I bring the 3 down in front and multiply it by negative 6. I get negative 18. I reduce the power by 1, negative 18t squared. Then 2 times 36 gives me 72t. And then t to the first becomes t to the 0, which is 1. 1 times negative 54, negative 54. Or you can just recognize negative 54t is a line with slope negative 54. So this is my velocity function. I get it from taking the first derivative of that position function. And taking that derivative should be something you're really, really good at now. In order to graph this, I again will find the zeros. I look at this, and in order to factor, those numbers look kind of big. So I look to see if any common factors, if I have any numeric common factors. And you certainly can see 2 right away because everything's even. But in 3, because everything adds up, 1 plus 8 is 9, so that's divisible by 3. 7 plus 2 is 9. These are all divisible by 3. They're divisible by 3 and divisible by 2. Means they're divisible by 6. It turns out these are divisible by 18. If you tried factoring out a 6 first, you would have found you could still factor out another 3 after that. So I factored out a negative 18 because I find it easier to factor with a positive squared value. Negative 18, and I get negative 18 t minus 3 times t minus 1. I'll leave that factoring to you. But in order for that to be 0, t is either 1 from this factor or 3 from the first factor. The negative 18 can never be 0, so we can ignore that. This is a degree 2 function. So the ends are going to go like x squared, except this is a negative, so the ends are going to go like negative x squared, going to fall to the left and fall to the right. And the other thing that's easy to graph, looking for things to graph, is you put in 0 for t and you get negative 54, so the y-intercept is negative 54. So when I go to graph this one I'll graph in a different color. So I have to put in my zeros. I have a 0 at 1. And I don't have 1 at 2, but I'll put a mark there and have a 0 at 3. And I decided my ends were like an upside down quadratic because it's a negative t squared. And that makes sense too, because I also found that way down here at negative 54, and it's probably further down than that. It's not to scale, and your graphs don't have to be to scale either. I go around, I cross at 3. I'm going to cheat a little and make that my 1. But you can see it goes about like that. But what's important is that I can see that this is at 1 and this is at 3 of my zeros. And anytime this graph is below the x-axis, it's negative. Anytime it's above, it's positive. And I can see also that at t equals 4, I'm still going to be negative. I only care in this problem from 0 to 4 because that's in the problem statement. So this is a good graph. I just have to graph from 0 to 4. You could have just plugged in numbers if you had wanted to. That's not the more sophisticated way to graph a polynomial, but if you're stuck, you can always do that. All right, so they wanted me to find and graph the velocity function. Here's the velocity function. I found it, and I've graphed it. So the next question is, when is the object stationary? The word stationary means not moving. Stopped. Even if just for an instant, it means it's not moving. If you're not moving, your speed is 0, so your velocity is 0. You're not moving, you have no speed, you have no direction, so your velocity will be 0. We already found the zeros of the velocity up here. We found they were at 1 and 3. So I've actually already answered that question in the process of graphing my velocity function. So that is when the object is stationary. The hardest part of this question is understanding what that word means usually. Stationary means not moving. And the next part of that question, I typed these out so you wouldn't have to look all the way back to the top, is when is it moving left and when is it moving right? The direction, okay, so direction is always the sign of the velocity. Negative is left, positive is right is the usual convention unless you're told otherwise. So it's a sign of the velocity. So when you hear about direction, you think, okay, I'm working with velocity. I'm working with the first derivative of position. So we had a graph of our velocity. It went something like this. That was a 1. That was a 3. Going up and turned around, came back down. Now, why is this graph helpful? This was our velocity function in feet per second. Well, a graph can show me the sign of the function right away. I know the value was 0 at 1 and 0 at 3. Until I got up to 1, though, my graph was, my velocity was negative. And then from 1 to 3, my velocity is above the x-axis, so it's positive, and then it becomes negative again. So it's moving to the left from here, from t is this to this, from 0 to 1, and again from 3 to 4. We remember we can end at 4 because that's what the problem told us. If the problem didn't tell us that, we would say from negative infinity to 1 and from 3 to infinity. Usually in these application problems, they restrict the domain. It makes the problem a little easier. And now, so that's where I'm moving to the left, and that's, I write that down here. That's as an inequality. Notice I don't include the 1 and I don't include the 3 because at 1 the velocity was 0 and at 3 the velocity was 0. That's neither positive or negative. So the object is stationary or not moving at 1 and 3, so that does not appear in these answers. And when I write them in interval notation, to leave the 1 out of the end, make sure I use a round parenthesis. Now in the middle, from 1 to 3, and again, not including the 1 and not including the 3, I'm moving to the right. I have a positive velocity. Right, for the next section, and you can always stop this video and take a break if this is going a little too fast. That's a little better than being in class. It's hard to stop me once we get going in class. Part C, we are asked to determine the velocity and the acceleration of the object at t equals 1. Well, we have a function for the velocity. That's okay. We found the velocity function in part B. And it's v of t equals negative 18t squared plus 72t minus 54. Well, this question is asking me to use t equals 1. So I just put 1 in and find the function value. And it turns out I get 0. Well, we knew that because when we looked back at where we found the object was stationary and how we found the 0, we get at t equals 1, the velocity was 0. We already found that in another problem. But if you didn't remember that you found it, right here in part C, you just plug 1 in and you do see you get 0, and that would be feet per second. They've asked me for velocity and acceleration. Some of the difficulty students have with this problem, if they're writing it out, is they don't do both of these. You have to read. Reading is as big a problem in this course as math is, and that's true in most math classes I teach here. So we've finished the velocity. We're good. That part's done. We need to find the acceleration. The concept here is that acceleration is the second derivative of position, but how do you take the second derivative? You take the first derivative and take the derivative of that. Well, we've already taken the first derivative of position. We call it velocity. So I just need to take the derivative of the velocity function to get acceleration. velocity is negative 18t squared plus 72t minus 54. I can use the power rule. Negative 18t squared becomes negative 36t when I take its derivative. 72t becomes 72. And then negative 54 becomes 0 because the derivative of a constant or just a number is 0. So here's my acceleration function. And again, I could go back and read the question. I want to know the acceleration at t equals 1. So I plug 1 in everywhere I had a t. I get negative 36 times 1 plus 72. I get 36 feet per second squared. Every time you take a derivative, it's like you're dividing by the x-axis units again. So you're dividing by seconds again. You take the first derivative, you get the y-axis units, feet, divided by the x-axis units once per second. That gives you velocity. Then you're taking feet per second and dividing it by seconds again to get acceleration. And feet per second is the same. If I do feet divided by seconds, it's the same as doing feet per second times 1 over seconds. Dividing by seconds, same as multiplying by 1 over, and that's where your feet per second squared comes from. You've probably seen that if you've taken physics. But anyway, the answer to that would be 36. Time is 1, acceleration is 36. Now, part D. This is a multiple step problem. You just have to unwrap it. Determine the acceleration of the object when its velocity is 0. So first you have to find when the velocity is 0, but you got to remember we did that, and maybe not in part A, it might have been in part B. We know the velocity is 0 at t is 1 and t is 3. So now they're just asking me to find the acceleration at 1 and the acceleration at 3. I actually just found the acceleration at 1 for part C. I did it out again here. You get 36 feet per second. And to find the acceleration at 3, everywhere you had a t in your acceleration function, you put a 3. And it turns out you get negative 36 feet per second squared. So you find where the velocity was 0, take those times and plug each of them into the acceleration function. Now, part E, I forgot to underline that in my notes here, but I'll underline it here for you. On what intervals meaning time intervals, the x-axis intervals, is the speed increasing? Speed increasing is a tricky concept for you to visualize because it could mean getting more negative. Speed is just the absolute value of velocity. So a bigger speed doesn't necessarily mean the velocity is higher on the graph. A speed of negative 36 feet per second is bigger than a speed of positive 20 feet per second. Because if you're talking about velocities, because 36 would be faster. It's kind of like, you know, if you're going 36 feet per second this way, you're going faster than somebody going 20 feet per second that way, even if, I should have drawn it the other way, but just the number is what matters, not the direction. Speed is a scalar, which means it's not a vector, which means direction doesn't matter. So how can we tell when that's happening? Because if velocity is getting more negative, it's going down. It's getting more positive, its derivative is negative. It's getting more positive, it's going up, so its derivative is positive. So it's not just a matter of looking at the sign of its derivative. You got to think about a little physics here. And what I want you to think about is this. If an object, if a car is moving this way, and we'll say that's negative. Maybe I should use an airplane, but I didn't feel like drawing an airplane. And its engine wants to go 20 feet per second. We'll stick with the same units. That's pretty fast, actually. And there's a wind blowing 5 feet per second. That wind does not increase the speed of the car. It slows it down. But if there's a wind blowing in the same, so if you're pushing something, if you want to stop this car, if you want to slow this car down, you're going to push it in that direction, in the opposite direction it's moving. Now, if the car is instead going this way, I haven't done a very good job of I kind of didn't draw the car backwards, but that's okay. If the car is instead going this way, if you push it this way, you're going to make it go faster. So if the push and the velocity are in the same direction, so if I went back to my car going this way, and I want to make that go faster, okay, so I push the car in the same direction it's going to go faster. Push is what causes an acceleration. So think of the push as the acceleration. If the acceleration and the velocity are in the same direction, either both positive, as in this case, or both negative, as in this case, then you are going to have a case where your object is speeding up. So for this problem, the easiest way to look at this is with a graph of both the acceleration and the velocity. So I'm going to graph them both on the same axis. And I just need 1, 2, 3, 4, because that's all my problem cares about is the first 4 seconds. So if I graph my velocity, I'll do that in red, and that's in feet per second. I had this situation, went down to negative 54 here, and it's going to come back through there, and it goes down here, and stop somewhere down there. So there's my velocity function. Now, if I graph my acceleration function was a line. It was negative 36t plus 72. That's going to equal 0. And that's of t. That's going to equal 0 at t equals 2. It's a line with a negative slope and a y-intercept of 72. So I have a y-intercept up here somewhere. The number isn't particularly important. This where it crosses the axis is important. So it crosses there because that's where the line will change sign. So if I partition this and I'm looking to see when the red and the blue are both on the same side of the x-axis, when the velocity and acceleration have the same sign. It looks like, let's see, I go from 0 until I get to 1, acceleration is negative, velocity is negative, acceleration is positive. So they're not the same. But here, the velocity crosses over. So it looks like from 1 to 2, I have the same sign on my acceleration and my velocity. They are both graphed above the x-axis from 1 to 2 seconds. So you can kind of draw little lines through all of the zeros of any of the functions, and it gives you intervals to look at. So I'm drawing lines through the zeros of the velocity and the acceleration. So I have to look from 0 to 1. From 0 to 1, I'm not speeding up because the signs are different. From 1 to 2, my object is speeding up because both signs are positive. From 2 to 3, the red velocity is positive, the blue is negative, so not speeding up there. But here, now the red is negative and the blue is negative, so from 3 to 4, I'm speeding up. So my object is speeding up on the interval from 1 to 2. And again, I do not include the endpoints because at 1 and at 2, it's neither speeding up nor slowing down. And from 3 to 4. It's slowing down from 0 to 1 or 2 to 3, but the signs of the velocity and the acceleration are the same. They're both above here and they're both below here, but notice both the red and the blue are below the x-axis, and here both the red and the blue are above. Here they're on different sides, so the object is not speeding up. Hopefully that little explanation about an acceleration being like which way you're pushing. If you push something in the direction it's already moving, you make it go faster. So if the direction is negative, and you push it in the negative direction, the sign of your acceleration would be negative. I hope that helps you understand these problems better, and please email me any questions.